The rapidly growing use of mobile devices such as smartphones have made mobile networks the most promising platforms for many brand new applications. The mobile network differs from traditional networks in a lot of ways, such as it has very high mobility and very unpredictable mobility pattern. So as the network becoming more and more complex and diverse, it's also becoming more and more difficult for us to learn important network properties, and therefore the need for finding new ways to learn the important network properties will become crucial. So when it comes to learning, we have to mention machine learning, and here is some basics about machine learning. So it is a discipline to design algorithms which allow the machines to evolve behaviors based on empirical data. So usually the behaviors in machine learning will be evolved either from training on data sets or from learning from past experience. So some popular machine learning techniques can be categorized in three subclasses. First, we have the supervised learning, including neural network or SVM, and we have the unsupervised learning mechanisms, such as the k-means clustering algorithm, and we also have reinforcement learning. So there are a lot of reasons why machine learning is playing such an important role in many different areas. For example, it can capture real-world complexity by being able to analyze very, very large amount of data sets, and it can tremendously reduce human efforts because it's mostly statistically based, and therefore it's very suitable for the automatic processing on the machines. And some machine learning algorithms also have the ability to adjust to the changing environment by incrementally tuning themselves. And machine learning have been used very widely to solve many different types of network problems, such as localization, tracking, or efficient job routing in networks. So now let me give you a very brief overview of the contribution in my dissertation. So in my dissertation, we focus on exploring new machine learning-based methods to learn important network properties and to solve network problems in the following aspects: performance, data management, and security. So it includes the following three problems. The first is the optimized gateway association problem, in which we implement a distributed access point selection scheme. And we also design a dynamic probing scheduling scheme to optimize the probing phase in the association particle. And the second problem is the Boomerang particle, which is a location-aware particle aiming to tie location-aware data to geographic locations. And in this scheme, we implemented a learning-based adaptive handoff scheme for a particular type of data aggregation, which is in-time data aggregation. And the third problem is identifying association. And in the third problem, we implement schemes, which is mainly statistically based schemes to identify different association particles based on the client's probing pattern. So due to the time constraint, I will be only mainly discussing the first two problems, but I will leave the third problem for offline discussion to anyone who's interested. So now let me first start with the first problem, which is improving access point association through bandwidth estimation and adaptive probing. So in this problem, we're interested in looking at scenarios in where there are multiple clients and there are multiple access points or gateways that the client can associate with. So the legacy association scheme is mainly based on received signal strength, and this scheme is known to cause load unbalancing problems because the only criteria that the client used to decide which gateway to associate with is the received signal strength from the gateway. So for example, in this scenario, because there are 7 clients that are basically closer to the first access point, and only 3 closer to the second access point. So these 7 clients will associate will choose to associate with the first access point, causing the load, causing the first access point to be congested, but leaving the second access point relatively idle. So a better scheme would be for the client to have some way to estimate or to learn the bandwidth estimation on these access points, so that it can make a better decision, and by not only looking at the received signal strengths, but also the available bandwidth on the neighboring gateways. So like in this case, a better approach would be for these two clients, A and B, to switch association to the second gateway, making the load on the two gateways relatively balanced. And so after combining the bandwidth estimation into the association process, we have the following protocol framework for our association protocol. So everything starts where the client is actively associated with the existing gateway. So while doing normal data transmission, the client will also estimate the available bandwidth with its currently associated gateway, and then it will constantly check whether the bandwidth estimation on the current gateway is good enough or not. And if it decided it's not good enough, then it will trigger the probing process, in which the client will start scanning all the neighboring gateways while also doing bandwidth estimation on these neighboring gateways. And after the scanning, after the client have collected all the information from the neighboring gateways, it will use a set of rules to decide which candidate to choose and what is a good time for the candidate to switch the association. And after it has made all these decisions, it will initiate the reassociation process, in which the client will exchange association management frames with the chosen candidate. And after the connection is established, it will resume normal data transmission. So we divide the protocol into two categories. In the first category is where we use bandwidth estimation in different data transmission phases to calculate the available bandwidth on either the currently associated gateway or on the neighboring gateways. And the second part of the protocol consists of a set of rules or decision-making criteria in which the client will use to make crucial decisions, such as when to trigger probing, which candidate to choose, or when to initiate the reassociation process. So let's look at the first part, which is the bandwidth estimation part. Here, the technology assumption is that we use 802.11 MAC DCF, which is distributed coordination function. So this is the complete frame exchange sequence, which is involved in transmitting a single data packet in the 802.11 protocol. So basically, it's a sequence consisting of the transmission of RDS, CDS, data, and ACK packets. So we can see that there are a lot of short time intervals involved in the sequence, and we group these short intervals into 4 categories, which is mainly used to facilitate our bandwidth estimation calculation in the following slides. So the last three variables are relatively simple. They are just the actual time to transmit the packets plus a short 6 interval, which is defined in the 802.11 protocol. But the TRDS is more complicated and worth more mentioning, because it actually includes the time, because it actually starts from the time when the RDS packet is put into the transmission buffer, and it includes the time that the client spent on contending for the channel So it includes the busy medium time and also the backup time. So therefore, TRDS is what we use to indicate the congestion condition on a certain gateway. And we can see in the following slides that this is a very important metric in our bandwidth estimation calculations. So now let me start with the first Orbital bandwidth estimation scheme, which is the scheme for calculating uplink traffic. So for uplink traffic, the client will initiate the transmission of the RDS packet, and we use this equation, which is using the size of the actual data transmitted divided by the total time to transmit this whole transmission sequence. So we use this as a per packet estimation for the effective bandwidth estimation on the gateway. And then in actual simulations, we actually use an average among multiple packets to get a smoother and more accurate result.
Is there a reason that you use the ratio compared to just the backup time, for example, or sorry, just to the backup time plus the channel busy time?
Okay, because I choose this because it's that's a very good question.
Did you compare them?
I think the reason I choose this because this is a more direct reflection of the effective bandwidth estimation, because this is really what we use to calculate the bandwidth estimation, the actual data amount being transferred, and the total amount of time spent on transferring not only the actual data but also the overhead involved in the data transmission sequence. So that's the main reason that I chose this scheme. But
okay.
And I think it's also easier to just use. It's also easier to just use this calculation because we only need to record, as shown in the second equation. We only need to, even so the equation is developed in this way, but we can later use a very simple equation, which is equation 2, to record the start time and also the end time. So
I see. Right, that makes sense.
Right, so we don't need to involve some other complicated recordings of the transmission intervals. Okay, and now it comes to downlink traffic. So downlink traffic is a little different from the uplink traffic in that it is actually the gateway who initiate RDS packet, and therefore the clients, if using the previous calculation, the clients would have no idea how much time does the RDS packet spend waiting to be transmitted. But we have some very smart trick by getting around that problem, which is to borrow the TRDS from the next immediate frame to the same client. So even so the client does not know how much time this RDS is spent waiting to be transmitted, it will accommodate that by shifting the sequence and including the TRDS from the next transmission, which is dedicated to the same client. And therefore, we'll again have the complete transmission sequence consisting TRDS, TCDS, TData, and TACK, and then have this equation to calculate the effective bandwidth for downlink traffic.
Let me see if I understood that. This time you're measuring is at the client that is sending the packet, or that?
So this is the time, right? This is the time when the client received the packet, received the RDS, and this is the time when the client receives the next RDS from the immediate next frame. So by immediate, I mean that there is no.
So this time is something that you can actually measure on an access point, or
no,
you're assuming that you can measure that?
These are time that we measure on the client side. You see, these are the time.
Oh, I'm sorry. Yeah, on the client side.
Right. So we have no idea what's going on the gateway side, but we can record the receiving and sending time for the packets from the client side, and that's what we use, like this T0, T1, and like in the previous slides.
How do you get that How do you get that T1 on the client?
So T1 is like after receiving this RDS, we know that this is a downlink traffic, and we are missing this TRDS, so we need to calculate another TRDS, and therefore we'll be paying special attention on the incoming traffic. And as soon as we see a TRDS from the same gateway, and we use this TRDS to form a complete transmission sequence. So this is basically the receiving time of the next TRDS on the client side. And I think that I need to explain a little more about what I mean by next immediate frame. So basically, so let's suppose this data packet has already been transmitted, but if there is no immediate next frame for this particular client, then the gateway might dedicate the time to transmit packets to other clients. So it is not fair to include all this sequence, to include all this time into this sequence to consist the transmission sequence. But if there is an immediate next frame, meaning that after sending the data to the client, the gateway has the next packet that the gateway is going to send is also to the same client. So we can basically just use the TRDS, because it's not sending to anybody else, it's still sending to the same client. So it goes through the same process of busy medium and backhaul, and all for the same client. So we can use this TRDS to replace this TRDS that we have missed to form a complete transmission sequence.
Does the client knows there is nothing in between? There is not a frame sending to another client?
There could be. So we need to check when we receive this, when we receive the data packet. So basically, the way for us to check is to see. So most of the time, the immediate next frame, the sequence of immediate next frames will come from the fragmentation of a very big frame passed from the upper layers. So in that case, we'll be able to check in the header of the packet whether this is a fragmentation from the previous packet. So if this is a fragmentation from the previous packet, then we know that this data packet is an immediate next frame to the previous packet, so that we can use this. We can include this TRDS in our calculation.
He's asking how does the client know the client is the only client?
Oh, it's not the only client.
There could so be that's not other part, right?
Right,
so
right. There could be multiple
clients. Because you made it
clients.
sound that's a requirement.
Oh, sorry about that. Yeah, there could be multiple clients in the scenario. So the gateway is also free to send packets to other clients during this time. It's just for this particular client, our concern is to find the immediate next frame dedicated to myself after receiving the previous data.
It's exactly the available downlink bandwidth for the client.
So your assumption is correct. It's like as long as it's a fragmentation of a bigger frame,
right,
it's supposed to be consecutively transmitted to the same client from
right,
the gateway.
Right.
Okay.
All right. Can I continue? Okay. So now it comes to the bandwidth estimation for the neighbor probing phase. So the bandwidth estimation in this phase is very important because we mainly use this estimation to evaluate the condition on the neighboring gateways during probing. So we can see that in the following slides, it is a very important metric. And when we look at the frame transmission sequence, we can see that it's actually quite similar to with the uplink traffic, in that the client initiates the frame transmission sequence. But the difference is that in this time, this time there is this extra probe request frame involved. So we need to make some adjustment to our equation. And after the adjustment, we come up with this equation 9 to calculate the estimation bandwidth for the neighbor probing phase. So that's about our 3 bandwidth estimation schemes for the different data transmission phases in the particle framework. And next, let's look at some simulation results. So here is our simulation setup. We use the Comet 4.5 simulator. We choose 802.11b as the phi and Mach layer particles. So we have these 2 gateways that are 150 meters apart from each other. And we have this dedicated area, which is 100 times 100 square. So the simulation topology is to generate a specific number of clients ranging from 3 to 10, and so for each configuration with the fixed number of nodes, we randomly generate 10 different topologies, meaning that we randomly generate 10 different locations for each node within this area, and then the radio range is 200 meters, meaning that all the clients within this area will be able to hear from both the first gateway and the second gateway. And the combined load of the station is set to the total capacity of the 2 gateways. So for example, if the total capacity, if the capacity on one gateway is 2 Mbps, then the total capacity will be 4 Mbps. And if there are 4 nodes, then the load, which is the maximum data to be transmitted on each node, will be 4 divided by 4, which is 1 Mbps. So now let's look at the result comparing our available bandwidth estimation based scheme with the legacy signal strength based scheme. So here on the x-axis is the number of nodes, and the y-axis is the average throughput on each individual node. So here, the dotted line, I don't know whether you can see this clearly, is shaped like this. It is the theoretical ideal throughput, and the orange line is the throughput of the signal strength-based particle. So we can see that the signal strength-based particle displays less average throughput and also large variance on the throughput, meaning that the load on the clients is not very well distributed. But when we look at the bandwidth estimation-based scheme, we can see that this performance is much better. It's actually very close to the theoretical ideal throughput, and the variance on the throughput is also small, meaning that the load on the clients can be very well balanced.
The total throughput is for these 2 gateways?
The total throughput, what do you mean?
Yeah, there's theoretical
so this throughput
right?
is actually the average throughput on each individual node.
And over that 2 gateway, right?
Right. Yeah, we assume there are 2 gateways available in this area, as indicated in our in the previous slides.
So I had a simple question.
Sure.
Simple. The signal strength based, is that similar to the auto rate?
To what?
Auto rate that you would have in a Linux Wi-Fi driver?
You mean by auto rate? Do you mean the node can definitely adjust their transmission rate?
Right.
According to the feedback?
Right.
Actually, we in this scenario we use fixed rate, which does not consider the adaptive adjustment of the transmission rate. So the transmission rate on the gateways and on the gateways will be configured beforehand and will stay that way throughout the simulation.
The clients are not mobile.
Oh, in this simulation scenario, it's static.
Okay.
Right.
If you use fixed rate, it's just the number of nodes associated with gateways matters. It's not actually the throughput. If you even the number, like if you have 6 nodes, 3, you get the best, right?
Right.
Because you use fixed rate. There is not, like, you're not using distance or single strings.
Right, but actually we, in our simulation, we randomly generate the location of the nodes, so we do not know. So we do not make any effort to divide them beforehand.
Oh, the fixed rate, but they using different rate. They could use different rate, like based on their distance to the gateway, right? Is that true? Or this?
The fixed rate based on...
What do you mean fixed rate? Is fixed rate for all the nodes or fixed rate for each individual node?
It's, I think by whether it's fixed rate or not, it means that the gateway can change the transmission rate due to based on oh, I see what you mean. So, so I think the scheme you're talking about is for the client to change the transmission rate based on the signal strength. So if the signal strength is bad, then it will reduce the rate. If it is good, it will increase the rate. But in our case, we use fixed. We don't have such kind of mechanism to change the transmission rate for both the client or the gateway. So the rate will remain the same throughout the simulation. Can I continue? Okay. So now let's look at the second part of our of the protocol framework, which is the gateway selection protocol. So this part of the protocol consists of a set of rules or decision-making criteria for the client to make decisions, such as when to trigger probing, which candidate to choose from, and when to initiate the reassociation process. So these two parts are actually heuristic based, and I would like to skip them due to the time constraint. So I'll only be focusing on the first part, which is a learning-based probing trigger. So what can happen during the probing phase? So far, we have been mainly talking about the benefits brought by probing, like the client may find, the main purpose for our scheme is to provide the clients to have more opportunities to do additional probing, so that they can find potentially better gateways to associate with. But the probing is actually a double-sided sword, because the time spent on probing, if you think about it, a client may have found a better gateway through probing, but it may not as well. So if it does not find a better gateway, then it means that the time spent on probing is actually wasted, which it could have used that time to actually do data transformation to increase the throughput. So, and if we look at some statistics about the probing phase, typical probing actually costs quite a lot of time, ranging from, on the average case, ranging from 0.1 to 0.2 seconds. And it costs even more when the network is congested, and even with the risk of losing connection. So therefore, we would like to have a smarter mechanism for the client to be able to estimate or kind of predict what could be the benefit or cost if I do probing at the current network situation. So that's what we come up with, which is a smart probing trigger for in which the client can learn from past experiences about the benefit or cost of the previous probing, and use that as an indication or a guideline for doing future probings. So the scheme that we use is reinforcement learning. In reinforcement learning, reinforcement learning is the process for agent to learn from past experience, whether it's a success or a failure, and it can adjust its behavior by receiving a reward or punishment. So a typical example is to learning to ride a bicycle. So at the very beginning, we learned that if you jerk the handle to far left or far right, will very easily result in a crash, which will hurt your elbow or knee very badly. So you will soon avoid to do such actions. And you will also learn about other actions that will actually result in fall. So after numerous iterations, you will eventually master the delicate maneuver of bicycle riding. And this is essentially a process for reinforcement learning. So there are a lot of benefits about reinforcement learning which cannot be replaced by traditional machine learning algorithms. So for example, it is an online learning algorithm, which means that the data is actually collected on the go, so that the agent actually have a much more updated data about the environment. And it requires less or none a-priori knowledge, and this is a huge benefit compared to the traditional algorithms such as neural networks or SVM, or even some of the unsupervised learning algorithms, because all those algorithms would require either a comprehensive model about the environment, or it needs to know or it needs to have a data set that's large enough to train the model from these data sets. But the data actually is not always easy to get, or sometimes it's difficult to get the enough amount of data to train the model. And reinforcement learning, on the other hand, can work very well in scenarios like this, because it gather all the required data while it gather all the required data online, and it can train itself through the ongoing interaction with the environment. So the reinforcement learning algorithm that we use is Q-learning. Here is the basic Q-learning model, which consists of a set of environment states S, and a set of actions A, and reward functions for state action pairs. So the goal of Q-learning, or any type of reinforcement learning, is to maximize certain long-term reward. In our case, the goal will be to minimize the long-term probing overhead, therefore to maximize probing efficiency. This is very abstract, but I will show how to apply the model into our problem. So here is our definition about the states, actions, and reward functions. For states, we have two different kinds of states. State S1 is when the current bandwidth estimation cannot meet the client's need, meaning that the client thinks currently the situation is not good enough. And state S2 is otherwise, meaning that the client is somewhat satisfied with the current situation. And there are also, we define the set of actions as the following. A1 is the action to initiate the probing process, and A2 is to refrain from probing. And here is the main point, is how we define the reward functions. So let's start with state S2, which is relatively more simple. State S2 is when the client is happy with its current situation. So in this case, by the way, the definition of Rij is the reward that we will get. Is the reward for doing action J when it is at state I. So for this R21, it will be the reward not to probe. The reward to probe, R1, which is A1, the reward to probe when at state S2. So basically the idea is, because currently we are happy with this current situation, then we would want to encourage the action which is not to probe, because if we do probing at this time, it will incur unnecessary overhead. So we want to encourage the action of not to probe by assigning R22 to 1, and discourage the action of to probe by assigning the reward function to A1 as 0. And this is basically the rule for defining all the reward functions in reinforcement learnings, which is to strongly encourage the action that is likely to result in a positive reward, and discourage the actions which is more likely to result in a negative reward. And now let's look at state S1, which is more tricky. State S1 is the state when the current bandwidth estimation cannot meet the client's bandwidth, cannot meet the client's requirement. So at this point, suppose we're currently at this T2 time point, and we find out that the current bandwidth estimation does not look good, so we'd like to decide whether right now is a good time to initiate probing. And so at this point, I need to mention that the client will actually record the timestamp for the past probings by recording the starting time and the finishing time for the last probing. So therefore, when the client is at T2, it will look at the previous probing and then see this T overhead time would be the time spent on the previous probing, and this T transmission time, which is the time since the finishing point of the last probing to current, which is the actual transmission, which is the actual time used to transmit data packet since the last probing. So therefore, we define R11, which is the reward function to probe, as T transmit times the bandwidth estimation since T1. And this is essentially the total amount of data that have been transmitted since the last probing. And we can see this reward function as the result we have gotten from the last probing. And then how we define R12? So R12 is the reward for not probing. If we did not probe last time, then what we would have done, we would have used this T overhead time to also transmit data, and therefore the effective time to transmit data would become T overhead plus T transmit, and we use this total amount of time times ABE at T0 to indicate the amount of data that could have been transmitted if we did not choose to probe last time. So therefore, by looking at these two reward functions, we can see that there are something that we encourage and discourage. So we definitely encourage a less. So for the action, which is to probe, we definitely encourage a less overhead time. And then for both reward functions, we encourage a larger value of ABE. So basically, it's the same rule for defining reward functions, which is to encourage the action that is more likely to result in a bigger reward, and discourage the action which is likely to result in a smaller reward. Okay, so now it comes to the quality function, which is defined in QSIAJ. So this is where Q-learning actually gets its name from. So QSIAJ is the value of state action pairs. For example, S1A2 is the predicted value or the reward for taking S2 when at S1. So we can see this is a very similar definition to the reward function. And as long as we have the reward functions, we have this update rule for updating the quality function iteratively. So this is essentially a value iteration with alpha as the learning rate. And we can see with bigger alpha, this quality function has a larger learning rate, meaning that it can adapt more quickly to the environment by putting more weight to the most recent reward functions. And now the policy for choosing action is as following. So each time when the bandwidth estimation for the current association falls below the bandwidth requirement, the agent will pick the action with the maximum quality function with probability 1 minus epsilon So making this policy a epsilon graded policy. And now let's look at the signature results. So we have this experiment. We have set up our experiment in this way. We have 2 gateways and we have multiple clients within this area. So, but we'll be only looking at the performance at this node A, and all the other nodes are used to generate background traffic dynamically on these 2 gateways. We have simulated on using 2 distinct load patterns. Let's now first look at the first load pattern. So in this picture, so in all 4 figures, the x-axis is the time, and the y-axis in this figure is the throughput on the access point. So the blue line is the load pattern on the first gateway, and the yellow line is the load pattern on the second gateway. So we can see that in this pattern, the load on the 2 gateways always, most of the time, will vary by a large amount, and we can expect that under such kind of scenario, the signal strength space protocol will actually suffer because it lacks the ability to dynamically detect the changing environment on the access point, and therefore will be stuck on the same access point throughout the simulation. So whenever whenever the load on one of the access points becomes larger, the signal strength space protocol performance will suffer, and which is exactly what is shown on the second figure. So the orange line is the performance of the signal strength, is the throughput of the signal strength space protocol. So we can see it dips whenever whenever the load on one of the access point becomes the maximum. But the 2 bandwidth estimation schemes, the blue line is the basic bandwidth estimation scheme, which does not involve the learning process, and the red line is the learning-based bandwidth estimation scheme. So those bandwidth estimation schemes actually is not affected by the changing load on the gateways, because it has the ability to dynamically detect the available bandwidth on the gateways. Therefore, it can dynamically adjust its association by always choosing to associate with the gateway with less load. And now let's look at the second load pattern. So in this case, the load on the 2 gateways are relatively the same. Right, and we just use one blue line to indicate the load on both gateways. So in this case, we can predict that the signal strength space protocol will not be affected too much, but our bandwidth estimation-based scheme, the basic bandwidth estimation scheme, will suffer because it will do a lot of probing, but the probing will not result in any good because the load on the 2 gateways are relatively the same. So through probing, it does not find any better gateway, and we'll have to stay with the original gateway. So therefore, it does not have any gain through the probing process except wasting the time spent on probing. So, and we can see in this result figure that the bandwidth estimation scheme, which is indicated in the blue line, performs worse than the signal strength space protocol. But the red line, which is the learning-based bandwidth estimation scheme, actually can perform just as well as the signal strength space protocol because it can learn from the past experience that probing in this network environment will not bring too much benefit. So it has the ability to refrain itself from excessive probing under such kind of network scenarios. And therefore, having the 2 results combined, we can say that the learning-based bandwidth estimation scheme will achieve best performance in both worlds. Continue? Yeah. Okay, so now a brief conclusion about the first part of the dissertation. We have implemented a distributed gateway selection scheme based on bandwidth estimation. We implemented the dynamic probing scheme by using Q-learning to schedule the timing for the probing process. Okay, so now let's switch angle to look at a seemingly totally different problem. Yes, we can still apply similar machine learning. Similar machine learning algorithms to solve. So this problem is Boomerang protocol tying data to geographic locations in mobile disconnected networks. So as new data services are being enabled by devices with sensing, communication, and storage capabilities, there is increasing need for transmitting and storing the data, which has location-aware interest. So, for example, the location-aware data can be used to detect and monitor road conditions, and can be used to distribute location-aware warnings about abnormal or hazardous road conditions. So we assume that so there are several challenges in the data collection methods in mobile networks. So let's look at several popular data collection models in existing networks. First is the centralized data collection model, in which all the mobile nodes will send its data to a centralized server through a common medium, and it is up to the server to do the actual data aggregation and data management. So this scheme, because it relies on a centralized server and common medium, the server and the medium always becomes a bottleneck for this approach. And there's also issues with the cost for storing the data and manage the data. The second scheme is the query response. Data collection type, in which the data requester will send a query to a dedicated, and then the holder of the data will respond with the data to the data requester. But this scheme, even though it works well in database systems, it does not work very well in the mobile network scenario, because in the mobile network scenario, due to the high mobility, it is very difficult to track the data source, and therefore there's no way for the data requester to know where to dedicate or where to distribute the data request. So here we would like to advocate the local aggregation scheme, in which we would want the data to be stored around the locations where they are generated, and we use short-range radios as the inter-vehicle communication medium to do the data transmission. So here are a couple of basic concepts used in our protocol framework. We have this anchor location, which are location of interest, where sensed data are generated or aggregated. And we have the geocache concept, which we use to refer the aggregated information around the anchor locations. And we use the geocache anchoring protocol, which we also call Boomerang protocol, which is a set of rules to hand over information through inter-vehicle communication as the nodes move away. So now let me introduce our implementation of the Boomerang protocol. Here we actually implemented two kinds of Boomerang protocol. The first is what we use as the baseline protocol. And okay, so let me first talk about the first scheme. So this scheme is the shortest distance-based selection scheme. So let me reiterate the purpose for the Boomerang protocol. Basically, the geocache will be basically, the main goal for the geocache, for the Boomerang protocol, is to maintain certain information around the anchor location. But the carrier needs to move, and when it moves away from the anchor location, at some point, to avoid the information from being lost, it needs to hand over the geocache to some other nodes with a bigger hope for the node to transfer the data back to the anchor location. So that's what the Boomerang protocol is about. It is a set of rules to find the candidate nodes to carry the geocache back to the anchor location. So with that in mind, we first have this shortest distance-based selection scheme, which we also call max progress in our when we present our simulation results. So here's how this works. We have the anchor location A, and we have the node that's currently carrying the geocache as B. So as B moves away from A, it at a certain point decides that it needs to transfer, it needs to hand over the geocache, because if it does not, then the geocache will be moving too far away from the anchor location and might get lost potentially. So now B, so there are several nodes that's surrounding node B, and the rule in the shortest distance-based selection scheme is to find the node that's 1, traveling toward the anchor location, and B, with the shortest distance with the anchor location. So in this case, there are D, C, E nodes available within B's transmission range, but B will hand over the geocache to E, because E is the node that's closest to the anchor location, and it's also moving toward to the anchor location. So here we use a differentiated handoff scheme to implement this procedure. Basically, B, whenever B needs to hand off the geocache, it will broadcast its geocache along with the anchor location to all its surrounding nodes. And only nodes, and the nodes receiving the geocache will check the direction, will check its traveling direction, and it will, so if it is traveling away from the anchor location, it will not consider this geocache. Only if it is traveling toward the anchor location, it will consider itself as a potential candidate for carrying the geocache. And now ECD has received the geocache. And then we have a differentiated backup procedure in which DCE will define a backup timer for themselves. And we define the T backup in a way that the nodes that's closest to the anchor location will have the smallest backup value. So in this case, E will have the smallest backup value, and it will set its timer. So they all set their timers at the same time, but E has the smallest backup value, so it will wake up the earliest and then send an ACK at the earliest time. And then now DE will receive this ACK and knows that there's someone else that is potentially a better candidate for carrying the gateway, for carrying the geocache. Therefore, they just they can ignore this whole request by stopping their timer, and then discard the geocache. And now only E will be keeping the geocache, so it will resume its travel and then continue this handoff process. There are some pros and cons with this scheme. So the pros are because this scheme is very simple, so it's very easy to implement this in a simulator. But there's some severe drawback in the scheme, because if we really look at it, the path that E is traveling, even though now it's the closest, even though now it is the closest node to the anchor location, it may not be traveling, it may not be on a path that will eventually lead back to A. But C, on the other hand, even though it is slightly further away from the anchor location, it is actually on the exact same path that node B has traveled, only in the reverse direction. So C actually has a much better chance to carry the geocache back to the anchor location. And
how do you deal with symmetries in this situation? Because if I look at that picture, wiggles see a tiny bit, and you assume that there was a road connecting E to A, sort of like in downtown Manhattan. C and E are almost the same distance to A.
Right.
And what if you have two nodes, C and E, who have the same distance to A? Thus, they would have the same backup timer, according to your calculations.
Right. Right, we actually didn't consider this scenario in our simulation, but we can use a very similar backup procedure, which is used in interview 11A, for them to enter a second round of backup, and then.
Oh, but now the second round of backup, node F, which was a little bit further away and happened to wait just enough, he sneaks in because E and C collided.
I'm sorry, what happened to node F again?
Node F's not in your picture, but node F was further away than E and C, but since E and C's acts collided, all right, they went back into another backup procedure. Meanwhile, F snuck in, or would sneak in, and it would actually then be the guys chosen.
Right, that's a very
I think actually, in this case for E and C, even if they're equal distance, but there is a little bit randomness in it. It's related to the distance, but there's some random factor, and she didn't mention that.
Okay. But they would still possibly, wait, so.
But there is possibility.
Is there a randomness that, the randomness is meant to deal with the fact that they might have collisions? Their acts might collide.
Right. So there is a possibility that you may not hear anything. In that case, you assume nobody in your neighborhood. Then you need to periodically send this out. But every time there's some randomness.
Right, but it still doesn't address the question which I brought up, which is E and C, for randomness or not, they managed to collide. Node F, which is not in the picture, slides in. And he was actually not the ideal choice according to this protocol.
That may happen.
Okay.
With a relatively small probability.
Yeah, I think
Depending on your deployment,
True, yes.
where the probability could be high.
Okay, that may happen.
Yeah, I think that's a very good point, because we actually didn't see this problem coming out in our simulation.
Well, our problem is always we don't have enough density.
Right.
So the collision probability is really low.
But in Manhattan, where there's taxis this way, continuously taxis this way.
That's right.
And
That's true.
everything is symmetric.
Right.
We
I
have-
guess the data we looked at were not that dense.
Right.
Okay.
Yeah.
So-
Yeah, and in the next slide.
So, is it necessary to keep a single copy of the geocache?
I'm sorry.
Is it necessary to keep a single copy of the geocache?
Yeah, we would like to reduce the duplicate copies for Geocache, because it's quite unnecessary, and it may cause confusion later on, because there might be uncoordinated or unsynchronized data entries in the Geocache. But actually, at some point, we also wish to keep some backup copy of the Geocache, just in case the original Geocache got lost. So it actually depends. It's not that we have to do a single copy, or we have to keep backup copies. So sometimes they will have benefits, but sometimes they will have severe consequences.
Could depend on the application.
Right. The application type and also the environment. Okay, so previously we have talked about the importance for considering the path that the geocache carrying node has traveled, and that's why we have implemented our second Boomerang protocol, which is the trajectory-based selection protocol, which we also call reverse trash protocol in our simulation presentation. So here, it works as the following. As the node is traveling away from the anchor location, it will record the path it has traveled in segments, which is defined by the turning points. So, and whenever it needs to hand off the geocache, it will broadcast the geocache along with the segmented path. And nodes that have received the geocache will compare its current look. First of all, they will look at their traveling direction. If they are traveling away from the anchor location, then they can just ignore this request. There is no hope for them to have a better chance to return the geocache back to the anchor location. But if they are traveling toward the anchor location, then they compare their location. They compare their self-location with the path segments. And then and then we use a very similar scheme which define the backup time. And this backup time definition will give higher priority to nodes that are on the earlier segments of this path. And for nodes that are on the same segment on the path, we give higher priority to nodes that is of shorter distance with the actual location. So therefore, that's how we choose the candidate node in the reverse trajectory-based selection to carry the geocache. Now let's look at the simulation results. We used the paramix synthetic traffic trace based on the Southern New Jersey highway system and traffic topology. So the figure on the left is, I guess many of you will see this very familiar. It is the highway topology of Southern New Jersey traffic. And we have the simulation results on the right-hand side. The x-axis is the radial range, and the y-axis is the return probability of the geocache. So we can see that when the radial range is really small, the max progress scheme actually does better than the trajectory-based schemes. This is because when the radial range is small, the potential candidates within the radial range to carry the geocache will also be small. So even so, the max progress choose, they might not be traveling on the reverse path. They may not be traveling on the reverse path, but at least the max progress have a better chance to find a candidate. But the trajectory-based scheme, they will ignore all nodes that are not on the traversed path. So it is much less likely for them to find at least a candidate. Therefore, when the radial range is really small, what matters is whether they can find a candidate, whether the candidate is qualified enough or not. But when the radial range becomes larger, the probability for the trajectory-based scheme will have a much better chance to find a more suitable candidate to carry the geocache further. And that's why, as the radial range increases, the performance for trajectory-based scheme will beat the performance with the max progress scheme. And now let us look at a particular type of handoff scheme, which is the in-time anchoring. So in this type of anchoring, the geocache is required to return the anchor location within a specific time frame. For example, a typical application could be we need to aggregate the vehicle speed within an hour, so we'd like to collect as many vehicle speed information as possible, and by the 1 hour deadline. The requirement for this type of application is that we would like to have in-time returns, and this is the dominating factor, because if we have a late return, then this statistics, this data that we have collected for all this time, we will not be able to include it in our calculation. So this will be a huge waste of resource. So in-time return is the most important factor. And other than that, once we are sure that we are in-time return, we also would like the return time to be close to the expected return time as possible. Because if the return is too early, then we might not have gathered enough data for the data aggregation. So we would like the return time to be as late as possible, closer to the expected return time, so that we can gather more data for aggregation. The more the better. And we actually have two schemes to control the return time, and the return time is basically tuned by adjusting the handoff time. So our first scheme is the additive adjustment multiplicative decrease scheme, and the second scheme is adaptive learning scheme using Q-learning.
That's additive, not addictive.
True. Oh. I hope your thesis has the correct spelling.
It's okay, it sounds the same. But one's
Addictive version would also be interesting.
She really loved grad school.
I hope we cannot have that in our paper.
Yeah, I'm good.
No, we need to double check.
Well, paper has been published, it doesn't matter.
People thought you purposely doing that.
Addictive. Okay, this has to be fixed.
Okay, so now let me introduce the additive.
Additive.
Okay. So now the additive, the AAMD handle policy. So basically, so the idea for these handle policies is to control the return time by adjusting the handle time. And in this AAMD scheme, we would like to compare the handle time with two things. First, we have a threshold rate, which is beta. It is a value from 0 to 1. First of all, we compare the return time with beta TERT. And TERT, I don't know whether I mentioned this or not, it is the expected return time, which is a requirement for this application. For example, we would want the geocache to be returned within an hour. And this 1 hour is the ERT in this example. So first of all, we compare T return with beta TERT, and we can use beta, for example, 0.8. So if the return time is less than 0.8 TERT, 4/5 of TERT, we consider this to be a very early return, and we have some confidence that increasing the handle time will not result in a disaster such as a late return. So we would like to additively increase the handle time by a small amount, delta. But if the return time is already larger than beta TERT, but it is still smaller than TERT, then we see this as there is a potential risk for this. There is a potential risk for the future returns to be a late return. So we would like to additively decrease the handle time just to avoid the disaster scenario of having a late return. And then if very unfortunately we do have a late return, we would like to dramatically reduce the handle time by dividing it by half. And then so by doing this, we would like to hope to get back to the normal in-time return scenarios as soon as possible. So that's what we mean by additive adjustment and multiplicative decrease. And now let's look at the Q-learning-based handle policy. So this is very similar to the scheme we presented previously in concept, but it has a much more complicated state and action sets. So this state 0 will represent the state of late return, which is this part. And then from state S1 to S5, we use them to represent different return times ranging from early return to close to expected return to on-time return. And we also define 4 actions. So for action 0 is the multiplicative decrease action, which corresponds to the action that we should take at state 0 for late return. And we have action A1, which is to additively increase TH, and action A2, which is to keep TH unchanged, and action A3, which is to additively decrease TH. And we define our reward function in the following. So this is a conditional decision term in which this term will take value 1 if the return time is less than the expected return time. But it will take value 0 otherwise. So if we look at the reward function, we can see again, it encourages the action that results in in-time return by assigning this term to 1. But it will punish the action that results in a late return by assigning this term to 0. And within the frame of in-time returns, we also assign larger rewards to functions that result in a close to expected return by keeping this term to S0. close to 0. So, and now it's pretty much the same. The rules to update the quality function, which is basically a value iteration process, and we have the learning rate, and the policy to pick the action is to pick the action that has the maximum Q value. And now comes to the performance evaluation. So we have presented two results. On the first, so the x-axis on both figures is the TERT, which is the expected return time. And the y-axis on the first figure is the ITRT, which is the in-time return rate. And so we use this to see whether this return is in time, to see how many returns are in-time returns. And then the y-axis on the second figure is T return divided by TERT, and we use this metric to see how close the return time is when compared to the expected return time. And we compare the Q handoff scheme with the AAMD scheme with 3 different delta values. So we can see that the Q handoff scheme, so the blue line is the performance of the Q handoff scheme, and this light orange line is the AAMD scheme with delta equal to 0.5. So we can see that the in-time return rate for Q handoff is smaller than AMD with a smaller beta value. This is as what we have expected because AMD will take a very aggressive approach to decrease the handoff time to prevent a late return, and therefore it can always result in a much higher in-time return rate. But we also need to look at the second factor, which is whether the return time is close to the expected time, return time or not. And in this case, again, the blue bar is the Q handoff, scheme, and then we can see Q handoff scheme actually achieves much more closer to expected returns when compared with the other 3 AAMD scheme with different beta values. Okay, so now comes to the contribution of the specification. We have implemented a distributed access point association protocol based on bandwidth estimation, and we developed Q-learning-based scheme to optimize the probing process. And in the second problem, we modeled and analyzed the trajectory-based Boomerang protocol and developed the adaptive handoff scheme for applications with specific return time requirement. And the third problem I didn't have time to present in today's presentation, but I'll be open to discussions offline. So in this problem, we propose the K-means clustering and Gaussian fitting schemes to identify association protocols based on probing patterns. And now finally to the acknowledgement, I would like to thank my two advisors, Professor Zhang and Professor Shetty. Thank you for your support and guidance and encouragement through all my years at Lab. So, yeah, this decision wouldn't be possible without your support, so really thank you. And I would also like to thank my committee member, Professor Kutiser. I'm very fortunate to have the opportunity to collaborate with you and benefit from your extensive knowledge on the vehicular networks. So
you actually read out what you wrote on your thesis. Very nice.
I'm sorry?
It was just a joke.
Okay, and also my outside committee member, Professor Chen, I really thank you for your warm support and your constructive feedback on the dissertation. And I would also like to thank my friends at Lab. So many of them have graduated, but some of them have not. But thank you especially to those who are here today. And you always make this place feel like home and very comfortable for me to stay. So I hope you can enjoy the rest of your study and research, and best luck to all of you. I would like to thank Lab and Rutgers University. So my experience all these years really made me learn a lot and help me grow, and I really appreciate this experience. And finally, to my family members, my husband, my parents, my daughter, none of them can be here today. But I really appreciate their unconditional support and love, and I cannot make it without their support. So really thank you, and thank you all.